All right, let's continue 3.7 and talk about inverse functions. First, I just want to talk about the informal idea of an inverse function. Two functions are inverses of each other if they undo each other. And this is a good pair of examples. If you look at f of x here, f of x is 2x plus 1. So if you think about what f does to the whatever its input value is, it says, let's take this x, let's double it, and then add 1. So f says double, then add 1. And g of x, if you look at what it says whatever your input value x is, subtract 1 from it. And then whatever you get there, divide it by 2. So these two things undo each other. Notice there's sort of two levels of the undoing that's going on. Over here, we double it and then add 1. Over here, we do the opposite of those things, and we also reverse the order. So we subtract 1 and then divide. So if you think of this as being, a step 1 and a step 2, we reverse those. The adding turns to subtracting, and the doubling turns to dividing, and we also flip the order of those two guys. So this is probably not necessary, but let's look at this. F of 3. If we plug in f of 3, we get 2 times 3 plus 1, which is 7. And then if we do g of 7, that's 7 minus 1 over 2. So 7 minus 1 is 6 over 2 is 3. So these two things do undo one another. All right. The more formal definition of this is it's really the same thing we just said, but it's just writing it out in notation. These two functions are inverses of each other if both f of g is x and g of f of x is x. So let's look at the example we had up here. Oh wait, I've got to copy that. Then I'll come down here and paste. All right, let's try that one more time. Yeah, let's just write out. F of x is 2x plus 1. G of x is x minus 1 over 2. And let's work both of these out. F of g, I'm going to go ahead and write it like this, is 2 times blah plus 1. And g is it's x minus 1 over 2. If you multiply the 2 through there, you wind up getting just x back. And if you do g of f of x, you've got blah minus 1 over 2. And the blah gets filled in with f, which is 2x plus 1. So the 1's cancel. You get 2x over 2. And you just get x. So these are inverses of each other. So some fun facts about inverse functions. A function f of x has an inverse if and only if it's 1 to 1. And we'll see more about that in a minute. We denote the inverse by this notation here, f raised to the negative 1 of x. Please don't confuse this with being the reciprocal. It's, I guess in computer science you'd call that overloaded notation. You got notation that means one notation that means two different things. But when you see a negative 1 on a function, it means the inverse function, not the reciprocal. Okay, this last part says, if AB is an ordered pair in the function f of x, then BA is an ordered pair in the inverse function. Let's go back up here and talk about that for a second. For this function f, actually let's go back up here. For the function f, if we think of an ordered pair as 3, 7. X is 3 and Y is 7. And over here for G, we're plugging in 7 for X and we're getting out 3. So if you go back to the sort of formal definition of a function as being a set of ordered pairs, you know, what it really means is this function up here, f, is the set of ordered pairs x, y, such that y is equal to 2x plus 1. And over here it's the same but with the other function. So you can think of a function as being a collection of ordered pairs, and the ordered pairs in a function are exactly the opposite of the ones in the in its inverse. So let's go back down here and look at this. That makes this example 2, 2, 1 pretty quick to do. Write out find the inverse of this function. Well, this function only has a finite number of pairs. So if this is our original function, we'll just call it f. Then our inverse function is going to consist of the ordered pairs 4, 0, 1, 1, 8, 3, 3, 4, and 5, 5. Now, this actually demonstrates why a function has to be one-to-one in order to have an inverse. Because, you know, down here, if we check this and say, is this f inverse, is this actually a function? Well, we have to look at all the x coordinates. And they're all different, therefore it is a function. So the requirement that this is one-to-one, the requirement that f is one-to-one, means is the same as requiring that its inverse is actually a function. Okay, let's do another example. This is a table that just gives us certain values of g of x. So if I wanted to use this to compute g of 0, I'd come over here to where x is 0, and the g value that goes with it is 2.2. And I'm going to do the same thing for these other two up here, where we've got g of 5 and g of 3. G of 5 is going to be 0, and g of 3, oh no, g of 3 is undefined. Why? Because g isn't defined for any value of 3. None of these guys up here are 3, so that one's undefined. All right, now to do g inverse of 0, what I need to do is come back up here and say, what value gives us g of x being 0? That's going to be 5. To find g inverse of 2.2, that's going to be 0. And g inverse of 1 is going to be 4. So if you're given a function table like that, you use it as a lookup table to evaluate g, and then you use it as a reverse lookup table to evaluate g inverse. All right, so far we've done 2 examples with functions, but these so far we're only given sparse information, just a handful of points, and down here, really this is really giving us the same sort of thing here. Each one of these things would be an ordered pair, 0, 2, 2, 1, 3, 1, 0.1, etc. But how do we find an inverse function given an equation? So I want to do a couple of examples of these. Here's what we do. If you're given f of x, what you want to do is first replace f of x with y, then you swap x and y. That's where it really goes from being an equation of the original function to an equation of the inverse. You solve that for y, and then you replace y with f inverse of x. So let's do a couple of examples. F of x equals 2x plus 5. We could probably figure this one out just kind of reasoning through it. But let's use this method up here. So first thing I'm going to do is I'm going to change this to y equals 2x plus 5. Now I'm going to swap my variables. X is 2y plus 5. And I changed color there because the purple is now the inverse. The blue up there was the original function. So you solve this out for y, you get, let's see, x minus 5 is 2y. Divide both sides by 2, so you get y equals x minus 5 over 2. And then the last step is replace y with f inverse. So f inverse of x is x minus 5 over 2. And that's it. Let's look at this next one. F of x equals 2/3 x plus 1/4. Well, first up, replace the f of x with y. Now swap the variables. And now we've got to solve for y. Now, what I would do here to solve for this, I think the easiest thing to do is to multiply everything by 12, because 12 is the smallest number that 3 and 4 both go into. So I'm just going to multiply the whole thing by 12. I get 12x is equal to, let's see, 2/3 of 12 is 8. 1/4 of 12 is 3. So I get 8y is 12x minus 3. So y is 12x minus 3, all that over 8. And instead of rewriting it, I'm just going to say this is equal to f inverse of x. And that's my answer. All right. I want to do some more complicated examples, but I'm going to save those for the next video.